And now moving on to 2.3, atomic structure and symbolism. So in this section, we're going to write and interpret symbols that depict the atomic number, mass number, and charge of an atom or ion, define the atomic mass unit or average atomic mass, and calculate average atomic mass and isotopic abundance. So in section 2.2, we ended by talking about the nucleus being discovered and neutrons, and that neutrons are about the same mass as a proton but have no charge. They're neutral, and these two are in the nucleus, okay, which is the dense center of an atom where most of the mass of the atom is. And then electrons circle the nucleus, and they're basically what makes up the atom's volume. It's mostly empty space because these electrons, you have your nucleus, and these electrons are just buzzing all around it. Okay, so if you were to take a quick snapshot, you have your nucleus, and maybe you've got kind of some electrons, something like that. Okay, but they're constantly moving around the nucleus. Now, an atom has a diameter of 10 to the negative 10th meters. Teeny tiny. The nucleus itself is about 100,000 times smaller than that. So it's a very, very small nucleus, especially compared to the overall size of an atom. So if we were to have an atom the size of a football stadium, the nucleus would be the size of a blueberry. Kind of trippy, right? Especially when you think about that gold foil experiment. If we were to take some tennis balls and we were all at the stands of the football field, and we were just chucking tennis balls, they would pretty much just go wherever in the stadium. Maybe 1 in a million practically would maybe hit that blueberry and be reflected. Kind of pretty crazy to think about, right? So let's talk about some units. Subatomic particles in atoms are crazy small. A carbon atom weighs less than 2 times 10 to the negative 23rd grams. Electrons have a charge less than 2 times 10 to the negative 19th coulombs. So we should have some special units for these because that's just a lot of negative exponents, right? Let's scale it down. So we have the atomic mass unit, or AMU. This is also sometimes abbreviated as just U. These are also called Daltons, which is DA. The U stands for Unified Atomic Mass Unit. So a Dalton, a Unified Atomic Mass Unit, and Atomic Mass Unit, all the same thing. So AMU, U, and DA, they're interchangeable. Daltons tend to be used in biology. Okay, so 1 AMU is equal to 1.6605 times 10 to the negative 24th gram. Okay, so it's basically 1 AMU is equal to the mass of a proton, basically, or the mass of a neutron. So the mass of a carbon-12 atom is 12 AMU. And the fundamental unit of charge, aka E, 1 E is equal to 1.602 times 10 to the negative 19th coulomb. So now we have our atomic level measurements. Like I said, a proton has a mass of 1.0073 AMU and a charge of positive 1. Now the neutron is 1.0087 AMU, slightly heavier than a proton. We basically round these to 1 as far as we're concerned. Neutrons have no charge, and then electrons have a mass of basically 0 and a charge of negative 1. So now our next term to talk about is the atomic number, which we use Z. So this is the number of protons that are in the nucleus of an atom. This is what defines an element. The number of protons tells us the identity of an atom. It doesn't matter if the number of neutrons or electrons are different. If it has the same number of protons, it is the same atom. Now, if we have a neutral atom, okay, so no charge overall, that means it has the same number of positive and negative charges. which means the same number of protons as electrons. So the atomic number also tells us the number of electrons in a neutral atom. Keep that in mind. This is for a neutral atom. Now, the mass number is the total number of protons and neutrons. So this is the approximate mass of this particular isotope of an atom. So we talked about isotopes being the same atom but with a different weight. This is where they differ, mass number. And if they have to have the same number of protons to be the same element, then that must mean that the mass number is, or the number of neutrons is what can differ. So we have our atomic number Z is the number of protons. Our mass number A is protons plus neutrons. And let's say I know my atomic number and I know my mass number. You do a mass number minus atomic number, and that gives you your number of neutrons. So it's not saying A to Z, it's saying A minus Z. I usually just do, like, I'll just say, like, AN for atomic number, MN for mass number. It really doesn't matter. As long as you know what you're talking about, you're good. So then the next thing is that protons and neutrons can be unequal in an atom, and this is called an ion. So this gives the atom an electrical charge when the protons and electrons are not equal. And the charge of an atom is equal to the number of protons minus the number of electrons. So if you have more electrons than protons, you have a negative charge. If you have more protons than electrons, you have a positive charge. And so our atoms, and even molecules, acquire charge by losing or gaining electrons. Has nothing to do with the protons, nothing to do with the neutrons. Those do not change in an atom. Only the electrons do. Okay? So if you have an atom that gains electrons, so that gives it a negative charge, it is called an anion. So if I have a neutral oxygen atom, so Z equals 8, it has 8 electrons. But if it gains 2 electrons, its charge then becomes 8 protons minus 10 electrons, negative 2. Now notice it says 2 minus, and this is actually how we write charges. So you could have 2 minus or 3 minus, 1 minus. This is how we do it. I really don't care overall. Sometimes I'll just write the charge as a negative 2. It doesn't really matter. If an atom loses electrons, okay, so it's giving away electrons, it's losing electrons. Now you have more protons than electrons. It has a positive charge. It's called a cation. The cutest ion there is. So this is how I remember. I'm a terrible artist. Cation. Cats are good. Anion. It's kind of one letter off from onion. Onions are bad. They make you cry. Cats make you smile. The Sprite makes me cry when she bites me. She's still a kitten and learning her way. Alright. So just to double down, cations have a positive charge. That's right. Okay, an example of how trace amounts of elements can make a big difference in our health. Iodine. So most of us, our salt is iodized salt. You want to make sure actually that you're not just using like pink Himalayan salt or black salt or whatever. You want to make sure that you have some iodized salt in your diet, because you actually need it for your thyroid, because otherwise the thyroid gland can enlarge, and this is called a goiter. And a little bit of iodine keeps this from happening. So we have all these different elements, right? And we saw the periodic table of elements in chapter 1 briefly. Before we get into the actual table, let's talk about the symbols that are on it. So a chemical symbol is an abbreviation that we use to indicate an element or an atom of that element. So for instance, mercury has the symbol Hg. Some symbols come from their common name in English, some from another language. So some of them are mostly from Latin. It tends to be the other language that some of their symbols come from. For instance, there you see Mercury. Most symbols are 1 or 2 letters. The 3-letter symbols are for some atomic numbers greater than 112. Don't worry about those. As far as we're concerned, our elements are 1 or 2 letters. Only the first letter of a chemical symbol is capitalized. So if you're writing the symbol for cobalt, it's C and a lowercase o. If you were to write CO like that on your exam, I would mark that wrong because you just wrote carbon monoxide, not cobalt. So if you're someone who tends to write your letters all the same size, you've got to start getting yourself in the habit of making it different for elements. So it doesn't matter how much mercury I have, Hg means mercury, means elemental mercury. So here's your book gives you a table of some common elements and their symbols and tells you where some of the interesting symbols come from. For instance, gold, the symbol is its symbol is Au from the Latin word aurum. And this is just a little nerd thing for me. I used to play the game Guild Wars 2 a lot, and there's a map called Auric Basin, and it's all gold and stuff. And it never clicked with me why it was called Auric Basin until like a couple months ago. I was just talking about how the name for gold comes from aurum to my class, and I just went, "Oh my gosh, how did I not realize this?" So, but it's important though that you notice that things like sodium is not S. Sodium is Na. Sulfur is S. Okay, so that you don't just assume the symbol based off of the name. So now let's talk more about isotopes. So we have different ways of writing isotopes to tell what specific one we might be talking about for an element. So generally you have the mass number as a superscript, which means up top corner to the left of the element symbol. And a lot of times you'll also notice the atomic number written as a subscript on the left. So they're showing you here magnesium's 3 isotopes, the general one. So what we could also do is Mg, and then the mass number, let's do it for 24. That's its mass number, and then its atomic number is 12, so that would go there. It's not, you don't always see it written with the atomic number because you're given the symbol. It's kind of repetitive to add the atomic number. But it's also helpful. For instance, if you don't know that magnesium is element 12, you wouldn't need to pull out a periodic table and figure it out. You go, oh look, here's my mass number, here's my number of protons. That means I have 12 neutrons. Another thing that'll happen is if you have a charged ion. Okay, so for instance, your book shows helium with a mass number of 4, atomic number of 2, and this helium, which this doesn't really happen, but whatever, has a charge of 2+. Actually, this does happen, just kidding. So the charge would then go in the upper right hand corner. Okay, so you have chemical symbol, charge, mass number, and atomic number. Oh, not, that's Z. Is your general structure. Oh, forgot this was here. Oh well. Hydrogen, for example, it actually exists as 3 isotopes. You have the regular hydrogen, which is called protium, deuterium, and then tritium. Tritium is bad. Very, very, very trace amounts to the point that you really can't even detect it. It's good. Tritium will kill you. Okay. So let's talk about a little bit more about atomic mass. I said this earlier, but each proton and each neutron basically weighs 1 AMU. As far as we're concerned, that's what they weigh, and an electron weighs 0. So the atomic mass of a single atom in AMU is approximately equal to its mass number. Approximately, okay? But most elements exist naturally as a mixture of two or more isotopes. So if you were to look on the periodic table, it shows you the atomic mass is an actual weighted average mass of all the isotopes. So in a naturally occurring sample. Okay, so this average mass, what you calculate to get what you get on the periodic table, is equal to the sum of the fractional abundance times the isotopic mass for every single isotope. For example, boron, I hope this isn't too boron for you. I said it. Boron has two isotopes. One with a mass of 10.0129 AMU. This is boron 10, and it is 19.9% abundance. And the other 80.1% abundance, boron 11, that weighs 11.0093 AMU. So the average mass, you take your percentage, put it over 100, turn it into a decimal, so 19.9 over 100 times its mass, 10.0129, plus the other one, 80.1 over 100 times 11.0093. And it adds up to 10.81. And what you should notice when you add these all up is that it looks somewhat similar to each mass. Okay, 10.81. So it's higher than boron 10, lower than boron 11, but a little bit closer to boron 11 because that one's 80% of the mass. Now, if I ask you on an exam, what is the average mass, and I give you these abundances and stuff, you better not add them up and divide by 2 or 3. Like, you wouldn't just add up these two atomic masses and divide by 2. If this were an in-person class, where you actually have to do things like show your work and whatnot, and I gave you this as a short answer question, when students do that, I usually give a lot of pity points, I call them. I give hardly any. I give like 1 or 2 for trying because I've specifically said don't do this. Okay, so take the percent abundance, change it to a decimal, multiply it times each weight, and each abundance times each weight, add them up. So here's an example. Meteorite found in central Indiana contains traces of the noble gas neon, blah, 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 blah. 91.84% neon 20, 0.47% neon 21, and 7.69% neon 22. What is the average mass? So we take our percent abundances, change them to decimals. So there's 0.9184, and that one was times 19.9924, 0047, and the 0769. Add them all up, and we get AMU of 20.15. So from this solar wind is 20.15, and this is just kind of a cool little thing. Terrestrial, so on our Earth, neon is about 20.1796 AMU. So different origins might have a different abundance of isotope. Kind of cool, right? I know I have a warped definition of cool. Nonetheless, this is how you do average atomic mass. Now you can also do kind of the reverse of this and figure out percent abundance or percent composition based off if you're given the average mass and you're given the actual atomic masses of the two isotopes. So for instance, we're told here's naturally occurring chlorine that consists of chlorine 35 and 37, and we're told the average mass is 35.453 AMU. And I want to know the percent composition of chlorine in terms of these two isotopes. So what this tells us is that my average mass, okay, so if you remember, it's the fraction of each one times its mass added up. So let's say we don't know the fractions of each one, but we do know that the two fractions of 35 and 37 add up to be 100%. So if I, for instance, I say that X is 35 and Y represents chlorine 37, those add up to 100%, or we'll just say 1 because we'll just do them as decimals. So that means that if I know the mass of X, I can find it because Y would be 1 minus X. Right? So now look, I've got an X, I've got 1 minus X, okay? So I know that the fraction of chlorine 35, we can call that X. Okay, so we let X represent the fraction of chlorine 35. So chlorine 37 has to be 1 minus X because that's the remainder of our isotope. There's only 2 isotopes here. And by the way, I'm not going to be some jerk and give you like 3 isotopes in a question like this. That's just mean. Okay. All right. So now I know then my average mass is 35.453 AMU is X times 34.96885 AMU. So this is for chlorine 35. Plus 1 minus X, representing the fraction of chlorine 37. That's what this, and this whole thing is representing chlorine 37. And then we do simple algebra to solve for X, and we get that X is 0.7576, so that means it's 75.76% chlorine 35. And so then the amount of chlorine 37 is 1 minus that 0.7576, 0.2424, which is 24.24%. And this makes sense when you think about it, because we were told the average mass is 35.453, and that's a bit closer to 34.96 than it is to 36.96. So it makes sense then that more of our overall mass of this isotope is chlorine 35. I know there should be 1 or 2 homework questions that are like this. So, mass spectrometry. This is something pretty close to my heart because I did quite a lot of mass spectrometry in my PhD work. What this does is we can use it to figure out abundances of isotopes and other work. So I didn't use it for isotopes. I used it for other work, but still. The way these instruments work is they vaporize a sample, give it some high energy electron beam that makes the atoms or molecules become charged, and they sometimes break apart. And then we can separate them by their mass and their charge in what's called a mass to charge ratio. So here's an example of zirconium breaking up and separating all its different isotopes. You don't really need to know much about this, just it exists, it's a cool instrument.